Thank you, everybody. I appreciate coming here. We've got 31 slides, but I go very quickly. So, yes, I'll take questions at the end. Probably the best way to do it, because I probably answer some of your questions as I go along. I call this GPS/GNSS 101. Boy, sexy title, right? Well, what is GNSS? You're thinking, never heard of that. You've heard of GPS. I'll actually explain how GNSS is what it's really called, and GPS is just part of it. So, we'll explain that. What is GPS? How does it work? What is GNSS? What are applications of it? How can we make it more accurate? Down to a few centimeters, in fact, even millimeters. What are the causes and how do you correct position errors? And also, I'll tie this into ham radio in a few ways, but you know, the impact of solar cycle 25. Who would have thought the ionosphere affects signals at 1.5 gigahertz, right? We're all familiar with signals being affected at HF, maybe 6 meters. You know, 1.5 gigs? Sure does. Every 15 seconds, it's affecting it. I'll explain that. Quick introduction to me. I've been around since doing ham radio since I was 15 in 1980. And got my first job with an engineering company that said, we want to hire somebody with advanced amateur radio credentials. I went, excellent. So I worked as an engineer until they figured out I studied marketing. But did RF engineering for a while. And I've been pretty much combining my work and ham radio hobby ever since. It's been very complementary, and I think that's just fantastic. And you know, a message that should be shared with aspiring students and ham operators. I'm apt to go active on everything from 160 to about 5.6 gigahertz. Yeah, really enjoy everything amateur radio has to offer. And time is everything. From GPS, which is all about time, as you'll learn, to music. I'm actually a musician when I'm not doing this stuff. So yes, you have to have good time if you're a bass player. So what is GPS? It's the Global Positioning System. Many of us know this. Okay. It was conceived of in 1973. They launched the first satellite in 78. It became operational by 1995. It's always fascinating with all these constellations, how it takes a long time from when they launch the first satellite till they really have it all operational with a full constellation. It's operated by, and I love this, the U.S. Air Force Space Command. That sounds like something right out of a sci-fi movie, right? But that's what it's called. And of course, it's was for military purposes primarily originally, but now it's used so extensively in the civilian world that there's no way they could ever flip the switches they had in the past where it was only available to the military. Okay. So we've got GPS, 31 operational satellites run by the US, and they're orbiting around 4 kilometers a second, 20,000 kilometers above the Earth. They orbit every 12 hours. I'll get into that a little bit more. They operate in several frequencies, pretty much between 1.1 and 1.6 gigahertz. And I'll actually look at the overlap with the ham bands and whether that's important. Yes. On the right, you can see a very crude spectrum diagram where L band, which is where the 1.5 gigahertz is just the rate of UHF. So just gives you kind of a sense of where things are. Okay, I mentioned GNSS at the beginning. What is that? Well, that stands for Global Navigation Satellite System. And that is actually what GPS is. It's a global navigation satellite system. You sometimes hear the term at IRU, RNSS. That's their kind of term for classifying as radio navigation satellite system. Same thing. Those of us in the industry, I work for a company actually based in Calgary, Hexagon, based right up Country Hills Boulevard in Deerfoot, even though I live in Vancouver. And where was I going with that? Well, we in the industry, we call it GNSS. And GNSS comprises not just GPS, the US the system, but also GLONASS, the Russian system, the Galileo system run by the European Union, and Beidou, the China system, as well as some regional ones. India has NAVIC and Japan has QZSS. Now, if you add all these up, you've got 113 global satellites and another, 14 to 18 regional ones. And there's actually a few more, but these are the main ones. And when you're using your phone, just as an example, or navigation in your car, and people say, oh, I'm using GPS. Well, yes, you probably are, almost certainly are, but you're also definitely using either GLONASS or Galileo or possibly all three. And increasingly, you'll see Beidou, the Chinese one, which is one of the newer ones. Now, there's some political aspects to this. GLONASS, of course, with the current situation with Russia, has become less popular, and iPhones and other Android devices that are moving away from it and towards using Galileo, which is also a more modern, fairly modern system out of Europe. So it's partly because more constellations is a good idea, and I'll explain why that is in a minute. But it's also because politically, countries are trying to avoid the risk of people that make navigation devices and people that use GNSS are trying to avoid relying on any one system that's run by a particular government, because it could get turned off or it could get scrambled in a way that makes the accuracy very poor. So that's why that's done. Okay, how high are the satellites' orbits? Well, we've got, looking at this diagram here, low Earth orbits, mid-Earth orbits, and geostationary or geosynchronous Earth orbits. So where are those? Geo, that's where most of the communication satellites are at, right? You know, you can put your TV dish and it's going to stay there because it's orbiting at the same rate as the Earth is turning, and that's 36,000 kilometers. The MEO area around 20,000 kilometers is where nearly all the GNSS satellites are today. But the emerging area for GNSS is LEO, low Earth orbits. This is where all the Starlinks are and things like this, the other things that you see flying by at night, Iridium and such. But there are two companies I'm aware of, there's actually several proposed that are launching satellites now for testing and going to be deploying LEO-based GNSS services starting as early as 2025. And why is this interesting? If you are in low Earth orbit, as you can see in the diagram, you only cover a small region, but you're a lot closer. You have a much more powerful signal. It's more focused. So it starts to work better indoors. It starts to work better under trees and difficult conditions. It also means that you've got these satellites whizzing by at quite a speed, and you can measure the Doppler off the satellite and use the Doppler to help refine your position. So interesting future ahead of us. Okay, this is the one that I always like this slide. How is position determined? Everybody goes, oh, the satellites determine your position. They actually don't. Satellites are pretty dumb devices, or simple devices, maybe politer. The smart stuff's all happening on the ground with the receiver. So let me describe this. Ignore the text for a second. Just look at the diagram on the right. Imagine instead of Earth and a bunch of satellites, that's like a soccer field. And I'm standing where that dot is, or the intersection is. I'm pointing at it as if you can see me pointing. Anyway, I'm standing where that dot is. And let's say, Lance is A, and he's over by the goalpost, and Justin's over at B, and somebody else over at C, and you're all at different places. And I say, okay, everybody, I know where you are. Throw a ball at me right now. That ball arrives at different times. I catch it from the three different people at different times. Now I knew where they were, so I know how long it should take for that ball to reach me if it's traveling at a known speed, and that speed is the speed of the radio signal, right? Basically the speed of light. So I'm like, well, they all threw a ball at the same time, but I got this one at this time, and this one at this time, and this one at this time, and I know where they were, so then I can calculate how far I am from each of them, and that's the circles you see on the right. So I know I could be anywhere in that circle, but there's only one place where I'm standing where all those circles intersect. And that's how you solve for position in GNSS. You actually get two positions, to be honest. So one of them, is not even on the Earth. It's way out in space. And so you say, that's the one I'm going to ignore. The one that's still left in the solution on Earth, that's where you are. So that's how it works. It's all about timing. It's all about the receiver receiving a time signal, a precise time signal from the satellites. And you know where you get another signal that tells you where each satellite is. And from that, you compute your position. So how many satellites do you need? I just mentioned 110 satellites on the other page. You only need 3, arguably, to get a XY position. If you want to do altitude, you need 4. But typically, we need a lot more than that to really have a useful position. And geometry really matters. This last point. More satellites, more constellations, more frequencies, these all equal more accuracy, because you can take more complicated measurements. But geometry is important. If you think about the example I just mentioned about the balls, okay, if everybody was right above me, if I'm in a city and I'm between tall buildings, I can only see a few satellites right above me, I get very poor geometry. The difference between one satellite and the other is very slight. But if those satellites are on the horizon and they're coming at me from the north, and others from the south, and others from the east, right? I'm getting very good geometry and measuring the timing arrivals. And that can be very hard to do in a city. And there's other reasons that are problems in cities like multipath, which I'll get into, but geometry is a factor. And I know some of you possibly joined this presentation that are on the ballooning group site I belong to, because a lot of us debate goes on about what is called dilution of precision. And that's really about, it's a measurement of satellite geometry as to how accurate your position is. Okay, I've spent way too much time on this slide, but hopefully now you actually can go and impress your wives after this meeting with, hey, honey, do you know how GPS works? Or your husband, as the case may be. Okay, modern uses of GNSS. We think of it primarily, probably in the early days, as kind of a classic sat-nav system in your car, and then increasingly your BlackBerry or your smartphone, right? But it's really ramped up now. I mean, GNSS is used in smart agriculture, like that precision farming tractor on the left, drones, self-driving or close to self-driving cars. The bottom right is something we do quite a bit of, especially in the North Sea and in the Gulf of Mexico, which is station keeping the they call it dynamic positioning, is keeping an oil platform right over the hole they're drilling. If you guys want to watch an interesting program on Netflix, it's called The Last Breath. It's a movie about a deep sea diver where the dynamic positioning system, which we were providing, but it wasn't our fault, spoiler, went offline, and the ship started to move as started dragging the diver across the bottom of the North Sea. Anyway, it's called The Last Breath on Netflix, and that's dynamic positioning, which is the use of GNSS. The other one I want to mention is the robots there, the Prime, that's called Prime Scout. We've been involved in this. This is they've got about 6,000 of these things that look a little bit like a toilet that they drop off in your area, and they from the van, and they go to all the houses, and you scan a QR code and the lid opens, and you take your Amazon delivery. That sort of thing, whether it's drones or robots, is using GNSS a lot, and it needs to be very accurate to avoid problems. Okay, so lots of it going on, but we talk about PNT, positioning, navigation, and time in our industry. Well, time is the other one. The time signal is pretty good coming off a GPS. Okay, it's not perfect, but I'll explain, but it's pretty good. So cell towers are all using GPS these days, or GNSS, to synchronize. A lot of data center equipment is using it. Measurement control systems, a lot of the power grid is counting on this precise signal. In ham radio, we have a few applications of timing on GNSS. One is stabilizing radios like the 9700, where you can take a GPS-DO device and get a 10 megahertz output, stabilize your oscillator. That's great. If you want a de-expedition and using a mode like FT8, we all know you need to update your clocks a lot. You haven't got internet, so you're going to use a device like that. We see this in the little FT8 diagram or a screenshot on the right, is delta time, DT, right? Milliseconds of error. You want to get that down as low as possible, and GNSS is used to do that. I actually have a remote station that I access over Arden, and I use GNSS to do that. Okay, we're going to talk about frequencies again. The reason I mentioned this is very topical. The International Amateur Radio Union is having discussions at I'm trying to remember if it's IRU or the ITU Geneva Convention. Anyway, there's the discussion about the fact that the 23 centimeter band, or 12, what is it, 1240 to 1296. Gosh, I should know. I've got a repeater on there. But anyway, our band overlaps with GNSS. And so there's been concerns raised by the GNSS industry about potential of interference from ham operators, and should they be restricted in power or frequencies and so on. And the latest I read a few weeks ago was that the submission from ARRL actually points out that there's not been a single case recorded of amateurs interfering with GNSS. So this is kind of a red herring, and we should really not all get panicked and limit amateur activity on this band, because it hasn't been an issue. And what I'll tell you guys, being in the industry and being a ham, is that any chance I get to protect our bands, I mention these kinds of things, which I've done for this and for the 5.6 gig band as well. Okay. But yeah, just kind of interesting. We are secondary on the band, as we know, right? So we do have to make sure we don't do things that are going to cause problems, but we're not, so it's good. Okay. Accuracy. How accurate is GNSS? Boy, I bet we've all had experiences where we've been driving and suddenly we're on the wrong street, or suddenly we're walking with our phone and suddenly we're trying to find our way to something, or we call the Uber driver and he's on the wrong side of the road. We're driving around the block because the GNSS signal was just not as good as it could have been. And why is that? It really depends on a few things. It depends on the quality of the receiver, the antenna, the number of constellations, the frequencies you're using, and the errors that are introduced. And I'll talk about what those errors are in some detail. But Quality receiver is a, you know, if you look at a smartphone, you've got about 6-7 radios in there with Bluetooth, Wi-Fi, cellular, you know, and GNSS, and you're trying to optimize all the antennas and receivers and avoid interference. It's a nightmare. The signal to noise in a smartphone is terrible, and so you really don't have a lot to work with, and you're going to have a real tough time getting high accuracy. On the other end of the spectrum, the company I work for sells receivers that are $14,000 that are used for survey work and things like that, that'll get you down to a couple of millimeters. So, you know, antennas and receiver quality. Timing, as I said, is everything. You know, 10 nanoseconds, so 10 billionths of a second delay in a signal means you're out by 3 meters, about 10 feet. So given a particular receiver and its limitations of antenna and so on, there's ways we can fix things by correcting what we call errors. And those errors are errors caused by multipath, orbit error, clock error, and ionospheric error, as I said at the beginning. Yes, even at 1.5 gigs. And also tropospheric error, which is a fancy word for weather, clouds and such, when the signals go through the rain and the cloud. Okay. So a smartphone, to answer the question, typically around 5 meters of accuracy. Everybody goes 5 meters, but when I walk down the street, it shows the dot right on the map where I'm walking. Well, what it's doing is it's saying, well, you're not going to be in the middle of a building when you're walking down the street. You're going to, or a field, right? You're going to be on the road. So it snaps to the road. And that's why it looks a lot better than it is. But that's also why sometimes, especially if you're in narrow streets and that in Europe and places like this, you suddenly end up on the highway beside the highway, right? High-end receivers are around 1 meter before they're corrected. When they're corrected, when those errors are corrected, now smartphones, tests we're doing in Calgary are showing results around 1 meter or better. And high-end receivers get down to a few millimeters. In fact, I did a driving test in a car in China. We're in Beijing, and I was driving around and I was getting 7 millimeter accuracy. Now, that is so crazy. Your antenna is about, you know, 10 centimeters across, you know, 15 inches or something, right? And now you have to decide for this measurement, what is the phase center of the antenna? What is the actual center of that antenna? Because you're measuring errors that are smaller than the actual size of the antenna. Okay, let's talk about these errors. Multipath. For us hams, this one's pretty familiar. We all know how this works on VHF, UHF, and so on, right? Reflected signals. It's not too hard to deal with multipath because if you've got two signals arriving at a receiver on the same frequency, the one that arrives second is reflected, right? The first one's the direct one. The subsequent ones are all reflections, so you can ignore them. So that's a fairly easy one to deal with, thankfully. Now this one, sorry for the little bit fuzzy diagram, this is called orbit error. So satellites orbit the Earth, obviously, right? But they're orbiting in an imperfect manner. Remember I said you need to know where the satellites are? Well, you can't assume they're gonna have a perfect circle around the Earth because the sun, the moon, and the Earth are constantly pulling and pushing on the orbit of the satellite. And there's even other things. There's air drag. There's even, I don't even have it in this slide, there's even the fact that the sun, if there's cloud cover, the sun will bounce off the cloud, and the photons coming off the sun, that radiation will change the orbit of the satellites. Now we're talking like centimeters of difference. But as I mentioned again, if you're off by a few nanoseconds, it's a big deal. So all of these things have to be dealt with. And I'll show you how we deal with it. But yeah, this is part of the challenge of accurate GNSS. The other one is clock error. The clocks on the satellites are not that good. I mean, they're better than anything you or I own, but they're still drifting slightly. In fact, they need updating every 10 seconds. They need to be corrected. And the reason is you can't spend the kind of money on an atomic clock that you're going to put on a satellite that you could on a reference station, you know, at WWV, right, where you're setting standards, right? So what you do is you do a pretty good job in space, and then you adjust it for any delta that you see against your atomic reference. Okay, there's other weird stuff. I'm going to talk about the weird stuff. Okay, Earth tide. Yes, as the moon goes around the Earth, it pulls, that's an illustration on the right, it pulls the Earth up. And it's measured up to 40 centimeters. The land that's directly below the moon is being pulled up. Just how it pulls tides, it also pulls the Earth. Continental drift. If you're trying to measure things against some sort of reference, which I'll show you how we do that, your reference stations need to be accurately measured. Well, they're drifting. The continents are drifting 10 centimeters a year. And then there's earthquakes that move things rather quickly. I was involved in a reference situation where we were monitoring the location of a station in Tokyo. There was an earthquake in 2011, and it moved The entire city moved 1.2 meters after that earthquake. So weird stuff. Okay. So let's go a little deeper in the ionosphere. And this is serious. This poor guy down here, he's really worried. He's chewing his nails off. Yes, it's serious. And I dwell on this a little bit more because this is the really fun stuff for me, ionosphere. And it's a big air problem. And it's also something that we can relate to as hams being actively using the ionosphere. Now, some of you know some of this, but probably none of you know all of this. Maybe some of you do. Anyway, you're going to hear it, hopefully. How does the ionosphere behave? Multiple ways in time, as we know, daily, as the sun rises and sets. We've all experienced that. 40 meters comes alive at night, 80 at night, right? Etc. 10 meters might go dead at night. There you go. Annually, we see cycles as we go through the 12 months of the year. And of course, the 11-year cycle that many of us are familiar with. Now, geographically, it's quite dramatically different too. So, where you are on the Earth determines how much activity you're going to see. And it's also, I don't know, we kind of describe this as kind of lumpy. It's like Eric Nichols, who's done a lot of research on this, described, I think, the ionosphere this way. It's kind of lumpy. It's not like as smooth as we think it is with layers, right? As you look through at an angle to a satellite and you transect or dissect a piece of the ionosphere or multiple layers of the ionosphere, you'll get something very different pointing in this direction than just a few degrees over in that direction. And if you think about the dynamic nature of the ionosphere, I mean, for those of you on HF, you kind of know this, but we don't, the best way to think about it is look at a shortwave station, right? An AM carrier, WWV, look at your S meter. It's moving constantly. It's not just moving, differently over an hour here, there. It's moving constantly. So we'll get into how we deal with that. Solar cycle 25. So let's start with the 11-year cycle. A few of you may have seen this in QST recently. The prediction from all the experts was that we would hit the peak of solar cycle 25 in 2025, coincidentally. In May of this year, we already exceeded what was forecast for 2025. So what does the rest of the graph look like for 2023, 24, 25? Not sure, but based on the trend so far from what you can see, it looks like we're heading into a more active cycle than anticipated. So this is going to be a factor. I love this graph because I always used to wonder why in October I get on HF and get all excited and I'll be talking to my friends, oh my God, this is gonna be great. Look at this solar cycle's fantastic. I'm working Europe on 40 meters, this is great. What's going on? And then it all get disappointing again towards Christmas. I'm like, what's happening? Well, this is the reason. We actually have in the dark red, that's the more intense activity. And you can see there's a spring and a fall peak. And I didn't know that till I did this job actually. And it's pretty cool. A lot of us know about this. Throughout the day, there's cycles, right? The regions split apart and they recombine again in the evening. Okay, so that's a factor, especially around sunset and sunrise, it gets a bit weird. There's also a lot of variation around the globe. This is a very important graph illustration in my business, which is if you've got precision farming in Brazil, which is a market that we service. So you've got people planting sugarcane, okay? They plant sugarcane, and when they plant it, they use GNSS to record where they planted the seeds. That is then used to fertilize, water, and harvest the seeds and the crop for the next 7 years, 7-year crop. Well, if you've only got about 2 weeks when you can plant, and if there's a storm, if there's a high level of solar activity, or you're in a solar maximum like we're coming into, your planted record might be all wobbly. It might be literally all over the map, right? You're going to be wandering. Your tractor's going to be wandering, and that's going to make your crop very inefficient for the next 7 years. So it's a big deal. So southern India, southern China, Indonesia, Brazil, these are really challenging areas for accurate GNSS. But we have ways to deal with it, which I'll get to. Now, just because we all live in the blue-ish area doesn't mean we're immune from problems. I'll even talk about a major problem in Quebec, going back to, I think, 2003. It's all relative. At solar maximum, it's all bad. It's all challenging. It just happens to be particularly tough in those red zones. And then, of course, we're familiar with solar flares and CMEs, right? I call them the tornadoes of space weather. They just show up with less warning than a tornado, frankly. I was in the CQWPX CW contest in May 26th, 27th. That is an actual picture of the solar flare that hit us that weekend on the left, that illustration. And that, I mean, that solar flare is, it's probably the size of about 400 Earths, right? It's massive. But that came and just killed us all on Sunday, and we just sat around, you know, chatting while we were calling CQ. It just killed the bands. But we probably know of this effect the most through, you know, auroral propagation and solar flare, or sorry, aurora borealis, northern lights, right? Very familiar with that. But it has a huge effect on GNSS because it's basically slowing down the signals is what it's doing. I think I have a graph on that. I thought it was earlier in the presentation, but I can mention it now. I remember I mentioned everything's about timing, right? Well, the ionosphere at 1.5 gigahertz, what it does is it causes a delay. It's not refracting the signals the way it does at HF, but it causes a propagation delay. So now you get a few nanoseconds or more of delay going when the signal goes through the ionosphere, and that's what messes up your position and throws you off by quite a bit. Okay, some large storms. The Carrington event, that's the big one everybody talks about, 1859. Sparks coming out of the Morse code keys, the one telegraph hut burned down apparently. People reading the New York Times at midnight under the aurora. Pretty crazy, right? That was a big one. 1972 in the Vietnam War, there were the U.S. Navy declared themselves under attack when mines started going off, and they realized it was their own mines that were being tripped by a solar flare, which was causing the contacts to close and the mines to go off. Crazy stuff. A few of us will remember 1989. I said 2003. 1989, yeah, Hydro-Quebec, when Quebec went down because of a solar flare affecting the grid. Remember I said it was for timing and running the systems? Yeah, that's what happened. 6 million people affected. And now, 2023 wasn't a solar flare affecting GNSS, but I kind of like this story. There's good videos online of, as a screenshot I took of 40 Starlink satellites going down because Elon Musk ignored us when we told him you shouldn't launch right now because there's a storm. And he said, I don't care. Okay, we won. You lost. You can't overcome these things. They're big. So what might happen in 2025? Hard to say, but it's going to be a challenge. Okay. So what's different from solar cycle 24, 11 or 10 years ago? Well, back then, some of us might have had Blackberries, I think. The first iPhones were just coming out. You know, there wasn't a lot of GNSS being used, and certainly industrially it was not as pervasive as it is now. Now it's used for a lot of infrastructure and safety critical applications, and increasingly is going to be used for self-driving cars. I can tell you guys that's a whole nother presentation, but I can tell you that starting in 2025, you're going to see a lot of them on the road. There's already quite a lot on the road that you're not aware of in the trucking business, but this is going to be a thing where we're going to have to make sure that it's safe. So what can we do? All this stuff's going on. We've got all these errors to deal with. We've got the ionosphere to deal with. What can we do? Well, the first thing you do, like our company does, and a lot of companies that are in this business, we set up a network of stations. There's an example on the right with a solar panel for backup and a cellular modem for backup and all this good stuff. And basically it's a high quality receiver, and you put them at locations around the world. Now we have, that map's kind of one of our networks. We actually have about, 8,000 stations, something like that around the world. We try to put them every couple of 100 kilometers in populated areas. And that's a lot of infrastructure. But the reason is the ionosphere, as I mentioned, changes so dynamically, even over small distance. I mean, I've got a remote station, maybe just 150 miles from here. And I see different propagation coming into there on HF than I do at my house with a similar station. So, you know, you can imagine for GNSS, with all the different angles you're looking at satellites and such, you need a very dense network. So that's the first thing. You need to get a bunch of stations looking at these signals in a known locations, surveyed locations, and say, okay, what are we seeing here that doesn't make sense? Why is this signal telling me I'm over here when I'm over here, right? That's part of the modeling. Then you take all those observations and you feed them into algorithms, and I won't go to this, again, a whole nother topic, but some of you might have heard of RTK, stands for real-time kinematic. That's one method for applying those looking at those observations and making adjustments for the user. And the other is precise point positioning, which is another model for creating a bunch of formulas or variables basically for all the errors that we talked about and canceling those out. And then what do? You need to get those corrections, as we call them, out to the end user devices. So this is a little bit of a, I don't know, what you call a little bit of an illustration of how that works. So reference network stations, I mentioned thousands of those worldwide on the left. Somebody like our company or others, process all that data, and then they deliver it to somebody like a mobile operator, Rogers or Telus or whomever, and they will then deliver it out to the devices so that when you turn on your maps on Google Maps, or you get in your self-driving car, or the drone wants to deliver the Walmart package to your house, it's receiving that data as a constant stream. It's updated roughly every 15 seconds. Again, primarily because of not, time is one issue, the clocks is one thing, but it's also just the frothiness, I like to call it frothiness of the dynamic nature of the ionosphere. So you're constantly sending these updates out to devices, and those incorporate that into their positioning engine to get you down to the situation where, it's safe to drive, it's safe to, you know where you are, you're not ending up in the wrong location. Yeah, I realized I was missing one slide, but it's okay. It was just basically saying what I said earlier about the fact that the L-band signal going through the ionosphere is what causes delays in that signal and causes the errors. So there you go. I hope I've given you a little bit of a learning about GNSS, a little bit of ham stuff, and a little bit about Cycle 25 and how it affects all that. I guess I would say more than ever before, and increasingly so, GNSS is now critical infrastructure. The storms are coming, definitely. We're heading into a big peak here, and but I think we're ready. Now, I will say one thing though: if you're sitting there in the cold and dark this winter because of a GNSS caused outage to the grid, they'll say, "Hey, but he said we could handle this." The truth is, there are going to be some storms where we literally cannot manage. And we've already experienced that in the last year. This year, we've had moments in our network and our services where you get an outage for 10 minutes, 20 minutes, even 40 minutes, in a certain part of the world. That will still happen. What we're trying to do, and other people, is to say, well, let's mitigate it as best we can, and minimize the impact as best we can, but it's never going to be 100%. The goal, though, is to try to avoid one of those Hydro-Quebec kind of outages where people are out for days shivering in their house in the middle of winter. That's the goal. And with that, I'll say thank you, 7-3.